So this is the first Silicon Valley Scala Symposium. Welcome. Welcome to Intel. Thanks to Intel for hosting us. Thanks for all the sponsors who made this possible and the volunteers who help us here. I'm just going to say a few words about the conference. It's going to be a whole day, and a few words about the history of this. So this is a SF Scala conference. It's basically Scala meetup in the city. I founded Scala for Startups 2 years ago. Then we merged with SF Scala. And this is basically the unified Scala meetup in the city. There is a fellow meetup now called Scala Bay, which used to be called Base. And we exchanged co-organizers with Vlad, who is the organizer. So essentially, we have a unified community, and we work very well with all the companies using Scala with type-safe speakers. So basically, Lily Masery, she is a Scala community organizer. She did 2 Scalathons in Philadelphia and had moved to the area in winter and had the idea to have the same thing here. And started this thing. And at some point, basically, she did a personal search and needed to take some time off to explore herself, and basically we had to pick it up, and we decided to do this in the rest of Scala. So the option was either to cancel it or to keep going forward, and the time was pretty short, and the date was already set. And essentially, we decided to do this, and essentially because of the meetup, because of all the speakers who did their presentations in the preceding years, I learned on Sunday that I have to put together the program, and by Wednesday I had 15 speakers, and in a few days I had 20 speakers. So basically, the program came together very quickly. We arranged everything, and essentially I think it testifies to the power of Meetup, and we're really thankful to all the speakers. And Meetup.com, by the way, is powered by Scala. So Nathan, the director of engineering of it, is a known contributor to a lot of projects. So that brings me to another theme of this conference. The URL is funconf.org, right? And the idea for funconf is something I had actually for a while. It's a fun conference. It's fun for functional in many senses, because it's functional with P and it works. And also it's fun, right? And if you look at a lot of speakers here, I think they succeeded in an ultimate goal of, I think, an intellectual person. They made their fun activity in the intellectual pursuit a profitable venture for them and the world, right? They basically found the synergy between what they like to do best and made it their job. So what we have in mind for the next year is to expand this idea of fun conference to several more areas, such as data mining, social graph analysis, and maybe some other areas, and maybe extend functional programming languages coverage to some other fun languages, such as Clojure. So we're going to think it through. But the whole idea, and I think one of the themes here, is this. And if you look at some of the top people in NFP community, I think you will notice, right? If you look at Josh Shureth, if you look at Rishiki, you will clearly see that they're having fun. They actually made a job for themselves doing what they love. And hope that can be one of the themes here. And I ask everybody, all the speakers who can, to play with stuff in the REPL, show how they do fun things, right? Because essentially, Scala people usually carve out a little niche for themselves. They start things as skunkworks, as side projects, and then they sort of gradually move it into the mainstream. And I think we're seeing this moment when Scala is taking over, it's becoming the industrial vehicle for many companies. I think the challenge for us is not to lose the spirit and really keep things fun. And I think that's gonna really keep the advantage, keep the quality of the community. And basically, that's the topic of the fun conference. So again, I want to thank our sponsors, Netflix. Jason Schwartz, he's one of the volunteers. He's manning a desk outside, or he's inside. And he really was instrumental in helping with the site and getting these wonderful little badges. If you need help at any point, ask one of us who holding this badge. The schedule is printed. Pick one up if you didn't. I sent an email yesterday with the plan. Essentially, we have 2 coffee breaks. We have lunch at noon, and it will be served inside. So after this, we all go to the training rooms, which are back. there down the corridor. There will be signs posted. We have to basically stay on course. It's a secured facility. We can only be in these training rooms, in the lobby, or in the restrooms. There will be signs for those. So there are 3 training rooms. There are 3 tracks. And each room fits about 50 people, and there is a common room for mingling and coffee. And one of my main requests was that coffee is infinitely available. So if it's not, you have to ask me or one of the volunteers, and we have catering folks helping out. They have to replenish it, right? That's extremely important for us that coffee is available continuously. So now I just want to ask Lily to come up here and say a few words because of her that thing started. Lily, you're here. All right. Can you speak loudly? I can mic you up. Here you go. You can just hold it.
Hi, can you hear me? Hi, everyone. Yeah, my name for the moment is Lily, Lilith and Flex. You probably knew me as UV. I organized Scala 1 and 2. So don't worry, it's more awkward for you than me. But you got to put yourself in Alexi's shoes like 2 months ago when he gets his email on it's Sunday night naturally, so he wakes up this Monday morning saying, well, you know, Alexi, I've decided I want to be a girl, and I don't really have time to arrange this conference anymore, but it'd be great if someone else could, otherwise it's kind of canceled. So we all owe like a huge debt of gratitude. I only set up the venue and just a couple basic things, all the food and sponsors had nothing to do with. So Alexi really put together something incredible, and I just hope you all join me in thanking Alexi for that.
And actually, it reminds me to mention that I think that's what Lily did is very courageous. It also fits this idea of fun as something you do best. You know, putting yourself and your personal project of yourself in front of jobs and deadlines. I think it's a courageous thing to do. It's very important, and I really applaud this. I think everybody should do this in the areas. If you find that you prefer Scala to Ruby, you're stuck in the Ruby startup. What you should do is not to keep slogging Ruby, but you should actually create a Scala company, and that's eventually what I have done. So and I was stuck in the Ruby place and organized Scala for Startups meetup, and then eventually, after a few iterations, selected Scala for a startup, and actually all our Scala team from Versal is here. I think I get 10 seconds to say that we're hiring. If you see any of the Versal guys, we have our uniforms on, talk to us. And now our awesome keynote. Marius Eriksen, I think, needs no introduction. He is the creator of Finagle. When I talk to Twitter folks, they invariably say he's one of the best Twitter engineers. And that's a consensus among basically everybody I talk to. And we're very fortunate that we got Marius as an advisor to Versal, where we use all Scala backend, and we're seriously thinking of taking the whole Twitter stack, starting with Finagle and then with Mesas. We have actually some talks in this conference, which will help everybody to see how we can do this. And everything he's done is extremely thoughtful. I think he presents distributed systems view as basically a new OS, a new computer. He thinks about it structurally. He basically systematically goes along the stack to instrument all the pieces, to provide profiling, protocol features when needed, and basically everything you can think about you need in a large distributed systems he already thought of, and actually not just thought, he works on it, and he contributes to open source. So I think that's the ultimate achievement, and we can only learn from Marius, and now it's off to him. So let's
cool. Well, thanks again to Alexi.
Make sure I think it's still right. Monica, are you getting this? Is it? Are you getting the signal?
Yeah. All right.
Because it's right here, but it should be. Okay.
I'm also going to turn on screen recording for posterity,
yes,
which we've been asked to do. There we go. All right. Oh. All right. Great. So yeah, thanks again to Alexi for arranging this conference. It looks to be excellent. I'm actually amazed that as many of you actually ended up showing up this early. I'm sure that we'll get more attendees as the day moves on. So what I'm going to talk about today is about concurrency and concurrent programming. And why I have sort of a long-standing obsession with concurrent programming in particular. And the central reason for that is that concurrency is sort of everywhere around us in what I consider sort of modern server software. And concurrency in general has been notoriously difficult to reason about and to sort of reconcile with programming languages. And furthermore, the kinds of tools that we consider state-of-the-art, so Java util concurrent, sort of threads and locks, semaphores, things like that, are really very primitive, sort of nuts and bolts things. They're very imperative in nature, for one, and they tend to compose very poorly. And so it's very difficult to write robust, good server software using what we consider today, or what the industry considers today, state-of-the-art tools. And there's another sort of there's another thing, which is that there's actually a really rich history of concurrent programming spanning all the way back to the 1960s, which have gone somewhat ignored, though not everywhere. There are things like Erlang and Akka and so on that have sort of dug up different pieces of history. But there's actually a lot more to it. And so what I want to do is I want to effectively give you a little bit of a history lesson and then sort of explore how we might use the kinds of ideas that were developed in the 60s and 70s in our sort of modern practice, and how in particular that fits into Scala. And Scala historically has been very sort of fertile ground for this. There's everything from, from obviously actors from very early on, which were taken from Erlang and so on and so forth. But a number of other sort of concurrency tools and primitives have been existing in Scala for a long, long time. And of course, part of that is because Scala is a sufficiently expressive language that you can create these DSLs and things like that. And so you can effectively create sort of higher order languages on top of the base language. So before I sort of get into the rest of the talk, I just want to make sure that we're sort of all on the same page when I say concurrency. So briefly, what I mean by concurrency is that you have a number of independently executing processes that communicate in some way. So this can be over shared variables. It could be over an Akka or actor channel. Things like conditions and queues, of course, also count. And what's really important is that these processes execute independently. Okay? And furthermore, we require non-determinism, right? And so what this means in particular is that every execution doesn't necessarily yield the same result. For example, if you have time dependence, you have non-determinism. And that's a very, very important property of modern server software. If you have concurrency without non-determinism, you're really talking about parallelism, and that's not what I'm going to talk about today. So again, why do we care so much about this? Well, first of all, most of sort of current practical server software interfaces with the world. You don't decide when a request from a client arrives at your server. You don't necessarily decide when a timeout from another system might trigger. You don't necessarily decide how long a disk seek is going to take. And so our environment is sort of highly non-deterministic. And you can't really control it. And this is sort of what gives rise to these tricky concurrency problems. Other interesting properties of our environment that are difficult to control are things like latency distributions. And of course, that goes all the way down to things like our network fabric and our processor architecture. So one way to view the sort of problem of why concurrent programming is difficult to do in the first place is that sort of our world, as well as increasingly these days our hardware, is highly concurrent, but our languages are sort of inherently sequential. We have semicolons, and we say, this happens and that happens. You have a loop that's deterministic. And the problem of concurrent programming is effectively trying to bridge these two worlds. How do we use this sequential language to interface neatly with this concurrent world and to be able to express concurrent systems using these sequential languages? And that's really what concurrent programming is about. And in particular, if we don't understand or can't reason about how we go about constructing these sorts of systems, we don't really stand much of a chance to have any sort of principled reasoning about our sort of modern server software. So before I go on, I want to sort of recall this quote from Hoare, which I think is, at least to me, has served as sort of a guiding principle to the FP community in particular, And he said, well, you can read it, I'll read it for you. There are two ways of constructing a software design. One way is to make it so simple that there are obviously no deficiencies, while the other way is to make it so complicated that there are no obvious deficiencies. And in my mind, this should really be like the slogan for the FB community, right? We try to create software that is just clearly correct, right? And tricky details like maintaining loop invariants and dealing with instantiating an immediate data structure and so on. We try to sort of relegate to implementation in the library language and try to really sort of surface the semantics of the program that we're working on. And so to me, this is sort of one of my guiding principles. So please keep this in mind as we sort of explore some history. And so what I'm going to do is I'm going to sort of take us through what I'll call 4 flavors of concurrent programming. We'll start with just a little bit of a review, not very much, of the sort of imperative concurrent programming. Then we'll go and explore what might you consider a more sort of functional way of programming concurrent systems. And after that, we'll talk about what I'll call process-oriented concurrent designs. And so this is things like actors and CSP and so on, which we'll go into. And then finally, I'm going to talk about what I'll call channel-oriented design, which is a variation of the process-oriented design, which gives rise to a lot of really, really neat properties. And I hope to spend sort of meat of the talk there. And in particular, I'm going to discuss what we call OperaBroker at Twitter, which is a concurrent abstraction that serves a lot of the good properties in what I call here channel-oriented concurrent systems. So first of all, let's start with the imperative. So before I sort of start explaining why this is so horrible, first of all, the good things about Java concurrency is that it really, really brought multithreading to the mainstream. And Java also defined a really nice and simple shared memory model, which helps in a lot of cases. And there's a lot of really good utilities. The problem, however, is that they're very sort of imperative in nature. They're very nuts and bolts. However, they map very, very nicely onto the underlying hardware and the hardware properties. And so as an implementation strategy, they're great, right? But they're not always the best way to write application programs. Here's one of my favorite examples. I'm sure lots of you have written code like this. Now, this is what's called double check blocking. It's sort of a pattern. And in order to really understand why this works and why you have to do this at all, it requires a really deep understanding of not only the Java memory model, but how that might interact with things like, well, in this case, locks. You have to worry here, of course, about, well, what happens if I call do something here under lock in this case? Are there deadlocks and so on? And this style of programming is sort of notoriously difficult to get right. And it composes very poorly. If I have well-behaved code in isolation like this, I can't necessarily take that well-behaved code and integrate it with some other well-behaved code. The result won't necessarily be well-behaved. Right? It gives rise to sort of unpredictable deadlocks, and race conditions and live locks and all these different things that are very, very difficult to understand. There are some more tasteful, what I'll call more tasteful uses of the sort of standard Java concurrency primitives. One is, for example, maintaining state explicitly. And so it's very, very common to, for example, use the various atomic operations to maintain an explicit state machine. And that can be a very, very useful tool. It's highly efficient. And in many cases, this is great. In many cases, this fits the problem very nicely. And it's a kind of pattern that you can use profitably. Now, again, the Java concurrency model very much emphasizes effectively mapping nicely to the underlying hardware. And while it does have a nice memory model that helps you out in a lot of cases, the subtleties around the memory model and how it interacts with the other concurrency constructs are often very subtle. It tends to be very prone to bugs, and again, as I mentioned, it's very difficult to compose. So the way I like to sort of think about these things is that these imperative tools are kind of mechanical in nature. You have to specify, well, how do I go about doing a particular thing? Not only that, but I have to say, how do I do it with respect to my environment and the Java memory model and the interactions between all the other agents in the system and so on and so forth. Whereas functional programming tends to be what I'll call descriptive, where instead of specifying exactly how you go about achieving a particular goal, you are closer to just specifying the goal itself, right? Not quite like to the extent of logic programming, but closer to it, right? And so that's the kind of terminology I like to use for these sort of things, like mechanical versus descriptive. So that was a short overview of the sort of current best practices Java concurrency. So let's revisit what it might mean to do functional concurrent programming. So what I mean by functional here is, as I highlighted here, sort of emphasizing immutability. Composition is very, very important. And so is sort of being able to isolate at least somewhat various side effects. And so when I say functional, that's the kinds of things that I want to emphasize and highlight. So there was a paper from the 80s called iStructure, which gave rise to what is now called Dataflow computing. And so Dataflow computing is the sort of ability to take an existing program as specified sequentially and effectively just insert threads anywhere you like. And the nice thing about Dataflow computing is that you can insert threads anywhere and the semantics of the program remain exactly the same. Right? And so this is what's called deterministic concurrency. And I said before I wasn't really interested in deterministic concurrency. The reason I'm showing this to you is will become clear in a second. And in particular, this requires you to operate in a language or with primitives that are determinate in nature, right? Like if I have, like for example, you can't have time dependence, right? Because if I insert a thread spawn anywhere, then if the scheduler decides to take longer in one run versus another, you don't have time independence anymore. And so you can't have non-determinate behavior. But it's anyway an important way to think about how to sort of reconcile concurrent programming with functional programming. And the basic idea is that you can sort of spawn off a subtree of your computation elsewhere. And this also plays very nicely with the notion of graph reduction. And so the way Dataflow languages, the runtime is implemented, is effective to do a sort of concurrent graph reduction. Now there's actually a dialect of Scala which implements Dataflow programming. It's called Ozma. This was presented at the Scala workshop this year. And it works in the following way. And so Ozma effectively introduces just exactly one new construct, which is called thread here. And anywhere you insert a thread, you're telling the runtime that you may spawn off this computation in a new thread. And what thread returns is just another value. It's not bound yet, right? And so this is how you would, for example, implement a concurrent version of mapping over a list in Ozma. And really the only difference between implementing it in a concurrent manner and a sequential manner is that you're inserting this thread operation for actually executing the function f, right? And so this to me sort of makes it obvious that yes, this of course has to be determinate, otherwise it wouldn't work, and so on and so forth. But it's also a very, very nice way of sort of reasoning about or reconciling concurrent programming with functional programming. You're just saying, I'm just going to execute this thing asynchronously. However, the values themselves, their types don't change. It just happens that it's not yet bound. And anytime I try to access that variable, or value rather, that binding, I have to actually wait for that computation to complete. And as I mentioned, this requires not only non-determinate or determinacy, but it also requires freedom from exceptions, which can be problematic. And there is some work in trying to sort of reconcile Dataflow programming with non-determinism. And Ozma, which uses a runtime called Mozart, introduces this notion of ports, which are effectively channels. And the idea is that channels are the only source of non-determinism in your system. And so what you can do to construct a system is to have these sort of independent pure parts that are sort of pure Dataflow programs connected by these dirty hoses that are non-deterministic. And together you get a non-deterministic system, but at least you can sort of easily reason about parts of it. And you have a principal separation of non-deterministic parts versus the deterministic part. However, I posit that in modern server software, basically any form of concurrency is non-deterministic. And so this sort of quickly boils down to using ports only. So this brings us to futures. And so futures are what I consider a compromise of Dataflow programming that allows you to embody non-determinism and failures and so on and so forth. The way to think about futures is that they're really just a container whose value is deferred, right? And so the operation that produces the value in this container is running asynchronously. And the future itself, is effectively a reference cell whose value is deferred. And you can compose them in a declarative manner just like we do with collections, right? And so I'm not going to go very deeply into futures because they're kind of a sideshow in terms of this talk. But here's an example of using futures, which I think very neatly illustrates the kinds of things you can do with them and why they're very powerful for composing concurrent programs in a functional or sort of functional way, emphasizing data transformations and so on. And so in this example, let's imagine that we have some trait page that represents a web page. And it might have a method called links, which gives us all the links on that web page. And I might have another method called fetch, which given a URL gives me a future of a web page. Now, if I was guaranteed that given a root I had a sort of pure DAG, then in fact this crawl method that I've defined here is completely accurate and works well. Right? And so the way to read this is the following. Well, first you fetch a URL, you take the result of that and fetch all of the links. You collect all of those into one future that contains all of the various links. So future collect is a combinator on future that turns a sequence of futures to a future of sequence of particular values. And then you recurse, right? And so there's a lot of really nice, this sort of demonstrates a lot of really nice properties about futures. First of all, you can use them in a way that's very, very declarative, right? In the sense that you're just saying, well, crawl, the definition of crawl is just to, well, fetch and then sort of fetch recursively all of the links of the page that you fetch. That's kind of the definition and semantics of a crawl. I haven't specified exactly how to go about this. Like I haven't said, well, first fetch this, then allocate this intermediate array to which I'm going to stuff all the intermediate results and create a semaphore that once it gets decremented to 0, I'm going to proceed to the next step and so on. And you sort of just specified what it means to crawl a page. That's very much in line with what I consider sort of good functional programming practices. Not only that, but you've specified nothing about the runtime. And so in fact, the runtime itself is free to adapt to the situation at hand. And this is something we use a lot in our RPC system Finagle, for example, at Twitter, where Finagle can, for example, determine, well, for this particular host, I'm not going to have more than this many requests at a time, for instance. So I'm going to limit the concurrency of this fetch to a given degree. Or I might decide to scatter all the requests across a number of threads, for example. This is something that you can implement purely in the runtime itself because you've sort of expressed the meaning of the operation crawl, not its mechanics, right? And this is very similar to having a sort of runtime that has a JIT, for example. A JIT can examine, well, actually this method invocation is always the same, and so I'm going to inline it. You can do similar kinds of optimizations when you separate the runtime from how you specify these kinds of operations. And that's very, very powerful. However, futures aren't without problems. And so futures present this very sort of ideal, simple interface where the result of any operation is just some deferred reference to the result of that, which again may fail. I can compose over failures. However, in real systems, this can often be problematic in the given sense. And so consider this example, for example. So I have, again, I'm just sort of using an HTTP client. I fetch a web page, or some URL rather. And the result of that is represented by the future f in this case. Now, within is a method on futures, which gives me a new future, which either fails within the given timeout, or succeeds with the result of f. Right? And so if f hasn't completed within 1 second in this case, g is going to fail. Now, the nice thing here is, of course, I haven't modified any of these futures. I'm just expressing g as a combination of timeout and another feature, it's sort of a pure immutable data transformation in that sense, right? I'm just getting a new thing that means a slightly different thing from f. And let's say I now wait for the result of g in this case. Well, if f takes longer than 1 second, then g will fail with an exception. And so I will, in this case, the printf here will throw an exception. And the result is no longer needed, right? There's nothing in your system that has a reference to f anymore, for example. Because of the way I combine these two things, I no longer need the result. However, the asynchronous operation that's doing the actual HTTP fetch in this case is still going on, right? And so this can be problematic, for example, if you have a server that becomes really slow and you're timing out most of the requests. Well, now you might have a retry on top of that dogpiles more work onto that, right? And so this sort of pure notion of a future that is this sort of like immutable container over which you can do transformations kind of falls apart a little bit in real life because of things like resource management and so on. And so that's kind of unfortunate. That's a sort of a very concrete problem with futures. And basically what that boils down to is that the producer and the futures aren't a channel, right? They're just a reference to some operation I might complete in the future. And this completely divorces the notion of a producer and consumer, right? And in particular, the producer doesn't know when a value is consumed or when a value is no longer needed, for example, which can cause real problems in real server software and so on when you use this in this sort of pure fashion. And furthermore, you can't really use futures because of their asynchronous nature to synchronize independent processes, right? So like, for example, imagine implementing a barrier. You can't really implement a barrier using futures only, right? Because you need the producer to know when a consumer has consumed a particular future and so on. And so while futures are very, very nice and present a very, very simple interface and way of reasoning about these kinds of problems, in reality, it turns out it's a slightly simplistic. So this brings me to what I call process-oriented concurrency. This is Hoare, by the way, Tony Hoare of Hoare Logic fame and so on. And concurrent programming, as I mentioned before, is really quite a rich field, and it started all the way back in the 60s. And at the time, people, Hoare and Dijkstra and so on, were sort of mostly concerned about how to formalize concurrent programs. And so Hoare Logic sort of presented a way to reason about, albeit in a tedious way, reason about sequential programs. However, Hoare Logic fell completely apart for concurrent programs because Hoare Logic would then demand you to effectively examine every single possible overlapping of executions and so on and so forth. And so that quickly fell apart. And so Dijkstra and Hoare in particular worked a lot on trying to figure out, well, how do we formalize how do we formalize concurrent systems so that we can prove properties and invariants and things like that of them? And I find this a very neat way to sort of, well, first of all, get a sense for how to sort of reduce a problem to its very essences. But it often also gives rise to sort of actually useful constructs for implementations. In particular, we've done this before with functional programming. Lambda calculus was constructed for similar reasons. So the first sort of seminal paper that tackled concurrent programs was one from Dijkstra called guarded commands. And guarded commands were basically Dijkstra's attempt to formalize and reason about non-deterministic programs. And we sort of established that non-determinism is, in this context, effectively equivalent to concurrency. And actually, I'm going to show you an example that shows very nicely why that is. So what this did was basically say, well, I am going to define an extremely simple programming language that has two non-deterministic constructs. The way I reason about this is these constructs maintain some sort of invariance, and I define a sort of calculus on top of this over which I can reason about programs and so on. And again, remember that these are formalization constructs. They're not meant to be sort of a surface programming language, but they highlight some important ideas. So the first construct in Dijkstra's guarded commands was this square bracket The squared bracket is called a choice operator. And you can compose it in the following way. You can say, well, if x is greater than or equal to y, or if x is greater than or equal to y, then assign x to m. If y is greater than or equal to x, then assign y to m. And so the first part here is the guard. It's kind of like a predicate that determines whether or not the second clause is eligible for execution. But the composition is non-deterministic in the following sense. So if there are multiple guard clauses that make the following statement eligible for execution, we pick one at random, right, in this case. And if there's just one, we pick that. If there's none, we just follow through, right? And so basically, this is like introducing a source of randomness, non-determinism, into your program. Now, that's sort of interesting, but things become really interesting when you put this in a loop. And so the semantics of a loop are the following. I'm going to execute the loop as long as there is at least one guard eligible for execution. The semantics of individual choosings are the same. And in this case, for example, I can implement a 4-slot sort in the following manner. And by the time they're sorted, then none of them are going to be true anymore. None of the guards are going to be true, and so they're going to fall through. The interesting thing to me about this example is that this sort of describes every single, like event loop scheduler, for example. This is a sort of proto-operating system scheduler, where you have a number of conditions that can be true or false at any given time, and you have to choose to execute one of them. The semantics of the operator itself gives rise to non-deterministic interleaving, right? So I can't rely on one getting executed before the other, and so on and so forth. And to me, this is sort of the essence of concurrency. So Dijkstra terms this non-determinacy, but really it's just concurrency, right? And it's in this way that I consider the two concepts basically the same. Another interesting thing about guarded commands is that they completely separated the language from the environment, introduced the notion of a runtime. Like a runtime has to be there to pick, randomly which particular clause gets executed for a particular iteration, for example. And so that's another interesting theme that comes up as well. So Dijkstra worked on guarded commands, and he sort of defined ways of formalizing about it. And a few years later, Hoare published an even more famous paper called Communicating Sequential Processes. And I think this one, probably most people have heard of at least. This is the famous CSP paper. And what CSP did was to extend on guarded commands in the following way. Instead of just defining a sort of a non-deterministic interleaving of loops and conditionals, Hoare explicitly defined the notion of a process. Processes themselves are independent and sequential, as I defined earlier on in the talk. And in addition to processes, Hoare defines what he called events. And these events are effectively interactions between various processes. So this can be sending a message or receiving a message. It can be sharing some sort of condition variable. And just like in the manner of functional programming, Hoare defined a number of combinators over these processes. So you can combine events and processes to give rise to other processes and so on and so forth. And we're going to go through this very, very briefly. So first of all, the kinds of events that exist in CSP, we're just going to treat these two events for the purpose of this talk. But basically, you can send a value x to process P with the bang operator and receive a value y from the process P with a question mark operator. And anybody that's done any sort of actor programming recognizes these operators immediately. And in fact, this is where that syntax came from. So the first way in which processes can be composed in CSP is what's called prefix composition. And so this is what in modern times we would call a semicolon, right? And basically what this is event A, which is usually some sort of communication. If that proceeds, then we become process P, right? And so now I've defined a new process. And so just as an aside, this is how you might write this in Scala, right? And so I might have some process P and some event A, and I create a new process Q by using the prefix combinator of A and P, right? And so I'm just creating a new process which has new semantics, but it's composition in the same way, right? It's just doing this sort of operating over these immutable data structures in this case, and just creating composite processes in this case that have different behavior from the underlying ones. And so I'm combining this event A with this process Q. And the semantics, again, is the following. So the process Q is the process which, when event A happens, it becomes process P. It behaves like process P. Another important composition that Hoare defined was interleaving. And so if I write P triple whatever vertical line Q, that is now the process that behaves like both P and Q at the same time, right? And so this is kind of like spying two threads. Now, interesting things start to happen when you introduce choice composition, and this is where Hoare borrowed most heavily from Dijkstra. And so choice composition is the following. The process, which is defined by A arrow P, choice B arrow Q, is the process that behaves either like P or Q, depending on which A or B is actually triggered, which event actually happens, right? And so now I can create these composite processes which diverge in their behavior depending on what the environment is like at the same time. And it's crucial to know that these are mutually exclusive. You know that exactly one of A or B happens as per the CSP semantics. And this is really crucial. This is a very, very important point, that these events are synchronous, so that communication occurs only when one process names another process for sending, and some other process names the same process for receiving, right? And so if I write P bang X, that's going to block effectively until somebody else executes P question mark Y, say. And just to really bring the point home, here's how that might work. Let's assume that we're dealing with some sort of discrete time system. Each dot in this diagram is a tick of time. And let's say I have two processes, A and B, and I get the combined process which executes them both simultaneously by saying A triple line B. If process A says B question mark Y, A is blocked until process B says A bang 1, 2, 3 in this case, right? And so process A is saying, well, I want to receive some value from B and bind it to Y. And process B later on says, well, I'm going to send value 1, 2, 3 to A. And this also works the other way, right? So if I try to send something and there's no receiver, I also block. And so when process B subsequently says A bang 3, 3, 3, B actually is blocked, right? Until process A agrees to receive something from B. So this is pretty simple, but I really want to drive the point home because this is a very, very important property, which you'll see in a moment. So the interesting thing is how synchrony in this case interacts with guards, as we've seen from Dijkstra. And basically, they interact in the expected way. And so you can compose things that are guarded, and as long as there are lots of things in your environment that want to communicate, exactly one is selected. And so, for example, this is how you might implement a semaphore in CSP. And so a semaphore is some process which defines a value V which starts at 0. If I receive a V message, right, from A in this case, then I'm going to increment V by 1. And by the way, this bracket construct with the star just means repeat this forever, right? And so this is a process which just repeats that body forever. And right, so if I receive a V message, then I increment V by 1. If I receive a P message and V is greater than 0, so this V is greater than 0 is a guard in this case, then I decrement V by 1. And so what that means is that process B can't grab the semaphore until process A has supplied some amount of values, right? And so this diagram is the same again. Imagine you have some sort of discrete time system. Each dot is a tick of time. Then process A might ask S for a slot in the semaphore. However, it blocks at this time, right? Because process B has not supplied it. V is 0. And so because of that guard, B question mark P is not eligible, right? And some time elapses, and process B supplies a v value that increments v plus 1. At that point in time, the second class becomes eligible, right? And now A is unblocked, right? And so the crucial thing here is that in some way, each of the clauses of this non-deterministic or this choice operator is a sort of latent event that is waiting in your environment, right? It doesn't actually trigger until it's eligible to as per the guards. And then so on and so forth. Now process B might supply another V, and that means that the next time that process A tries to get a P, he doesn't block anymore. Right? And so the crucial thing here is that these events are these sort of latent things that your environment controls, and they're synchronous. And this is a really, really big idea. And I hope to try to convince you, if there's nothing else you remember from this talk, I want you to remember about events. And I hope to, in some subsequent examples, show you why. And I'm going to show you Scala now, not some sort of obscure, outdated syntax. But basically, the environment is responsible for, well, you have a bunch of events in the environment. You can think of it as a big sort of chemical soup. And the environment itself is responsible for sort of matching events that are sort of eligible for rendezvous subject to the guards that they specify. And this combination turns out to be extremely powerful. In fact, you can think of this as the environment effectively doing a transaction for every time tick, right, on your behalf. So if you remember nothing else, remember Dijkstra, Hoare, guards, and events. As a short aside, actors are also structured around, actors are familiar to Scala programmers. They're also sort of structured around processes. And I've heard from many sources, actually, that they share lineage with CSP. That's actually not true. They come from Carl Hewitt, which actually predates CSP. And in particular, actors are asynchronous. And so they don't have things like guards. And they don't allow you, you couldn't, for example, implement using a simple actor API, things like barriers and semaphores, which I've shown you, which gives you some idea that this notion of CSP is different and maybe also more powerful. Right? That being said, actors are wonderful for doing things like network communication, where asynchronous is paramount. Right? And so finally, I'm going to go over now what I'll call channel-oriented asynchronous programming. And what I mean by that is the following. And so if you remember in CSP, we dealt primarily with processes. We had we combined processes and events to create sort of composite processes, which had sort of different behavior. We had this environment that made sure that processes rendezvoused when they were eligible to. And the thing to remember about CSP is that it was constructed in order to formalize over. And in particular, the number of the processes themselves were lexically bound. You couldn't have more processes than you can define tokens in your lexical environment. So that obviously is problematic for a real-world scenario. It's not a very flexible way to write a program. On its own, it became a very, very cumbersome programming model. There were some people that tried to make it into a real language, but it turns out to be very cumbersome. So what I call channel-oriented concurrent programming is basically CSP, but making the channels not the processes first class. And so in CSP, if I say, send this value to process A and receive that other value, or send that value to process B, and B receives a value from process A, I can then share a channel over which I can send and receive at the same time, right? The semantics are actually very, very similar. It's more difficult to formally reason about it, I think. But it turns out that it's a more flexible way of doing actual programming. One concurrent programming system that makes use of this is something called joint calculus. And again, joint calculus takes the sort of core ideas of CSP, or some of the core ideas of CSP, not all of them, as we'll see, guards and channels, and effectively defines this environment that is responsible for rendezvousing things, right? And so one way to think about that is that your environment is a big chemical beaker, okay? And each channel represents some ingredient, right? And so when I send something on a channel, that means that that ingredient becomes available in your environment. And reactions are defined as, well, in order to create some y, I need an x and a z and a b, right, for example. And so you can create these sort of declarative, what they call joint patterns in joint calculus, to effectively decide how reactions proceed in your sort of big chemical beaker environment. There's a language based off of OCaml called JoCaml, which makes use of this. And this is a simple example of, for example, doing a concurrent stack. And in this case, we sort of have all the components that I've talked about, except for synchrony. And so the way to read this is the following. A stack is something that defines 3 channels, a state, a push, and a pop. And there are 2 quote-unquote reactions defined here. If I have a state S and a push, so if there's both a state events available and a push event available, then that creates a new state event and replies to push. And so it tells you that the push succeeded, right? Or if there's a non-empty state available whose head is X and a pop operation available, then I produce a new state, S, which is the tail of that list, right? So this is just as in Scala, you can deconstruct and construct lists in that way, using this exactly the same operators, and reply with the head of the list to the sort of pop channel in this case. And the important thing here is that these things are mutually exclusive. You know that at any, if you sort of think about discrete virtual time, at any tick, exactly one of these happens, right? And so you define here that state can only be modified by one of these at a time. And it's not exactly modified, you're sort of defining it as producing a new state in your environment. And these quote-unquote reactions happen only when you have both a given state and a push or pop operation. And this example also uses guards, right? Because the second clause here is not eligible for execution if the list is 0, if the list is empty. So now the question is, well, we have a primordial soup, if you will, now of various abstractions and ways of thinking about concurrent programming. And the question is, can we make use of this in a practical way, say in Scala? And it turns out that there's a dialect of ML called Concurrent ML, which attempts to do just that. And at Twitter, we created something called OperaBroker, which borrows a lot from CML to basically try to figure out how to employ these ideas, in particular synchrony, guards, and channels, in a practical setting, one that we can actually use. And we call that OperaBroker. So an offer is, again, some sort of abstract value over which you can sync. And so a synchronization operation is, and its name implies that it's synchronous, allows you to retrieve a value t from offer, right? And so when you synchronize an offer, that means that you're effectively saying there's some event in the environment that that you want to retrieve a value from, and you can do the other sort of all the other kinds of things that you might do with containers in Scala, like for example, you can map over it and so on. Now, critically, now that we have this sort of abstract notion of an offer, and you can think of offer as an event, right? And so when you look back at CSP, an offer might be represented by A bang X, that's an offer of sending something. B question mark Y is an offer of receiving something, right? And only when you call synchronize on these offers do you actually sort of actualize the fact that you do want to synchronize on it. Offers by themselves are just values that don't do anything, right? And crucially, you can compose over these offers. And so for example, I can take a number of offers and use the offer.choose combinator to create a composite offer which does exactly what choice in CSP did, which is to say exactly one of those offers synchronized, right? Select is just a shorthand for calling choose over a set of offers and synchronizing. It turns out this is just a useful pattern. And then there's sort of sundry offers that are useful. For example, you can define a timeout offer, which is an offer that's willing to synchronize after the given timeout. A never offer is an offer that never wants to synchronize. A constant offer is one that will always synchronize with a given value. And so now the question is, we've defined this sort of abstract notion of an offer. They're just these sort of events that you can synchronize over and combine in certain ways. So now the question is, well, I need a source of these offers, and that's what we call brokers. And so you can think of brokers roughly as a kind of a channel, right? And if I have a broker of type T, I can call send, and send gives me an offer of unit. And so if I have a broker B and I call send, I get an offer over which I have to synchronize in order to actually sort of actualize that event. But I'm just creating these events that I can combine and synchronize later. And this is how you might want to use that. Let's say I have a broker of integers. Well, if I call B send 1, 2, 3, that doesn't do anything because I haven't synchronized over it. However, if I synchronize over it, then I block until some other process has received it. And so this is a sort of rendezvous going on. And conversely, if I call B receive sync, then that blocks until there's some sort of sender available. This is just synchronous communication as we defined earlier. So now you can start doing some interesting things. So remember the semaphore from before. This is how you might define this in OperaBroker. So I have a P and a V broker, right? And if I receive a V event, then I want to increment my semaphore value. And if V is greater than 0, and I receive a P event, then I want to decrement my value, right? And so now I've only used what I've showed you, right? I'm using a broker to represent the sort of channel of sending P and V messages. And I'm using offer select. Remember, offer select is just a way of doing offer choose and then synchronizing on that, right? And this is now a semaphore. And the semantics of offer select guarantees that these two clauses are mutually exclusive. And furthermore, you have guards naturally because you can just use the full power of the Scala language to examine whatever condition you want. And in this case, for example, if V is not greater than 0, then I'm never willing to receive a P event, and so I just call it, I just give it an offer.never instead, and combine that with a V receive event in this case. So this is what a semaphore looks like in OperaBroker. You might define a resource pool, for example, to be the following. I might define a broker for getting and putting items into this resource pool. The pool itself might be represented by a queue. And the way that works is that, well, if my queue is empty, then I'm not willing to send anything on the get channel. However, if it's not empty, then I'll send the head of my queue, right? And if that actually ends up synchronizing, then I recurse on myself with the tail of that queue. I'm always willing to receive a put event, and then that means I recurse again with that element that I just received and queue onto my queue, right? And so in this, again, now we're combining this mutually exclusive choice operator with synchronous communications with guards, and it gives rise to some very powerful things. Now you might say, well, this is not so interesting. This is just a pool. Anybody can define a pool. You can have locks to do the same thing. Just synchronize a critical region. Like, this is not very interesting yet. However, when you actually start using it is when it gets really interesting. So for example, let's say I want to just receive an item. Well, that's pretty boring. I can just call get receive sync. That synchronizes on the receive event from the get broker in this case. However, let's say I want to wait for no more than 1 second to get something from my pool, right? And so if there's nothing available, after 1 second, I just want a timeout. Well, then I can define a timeout offer. Recall that's now the offer that is willing to synchronize after 1 second, and combine it with my receive offer. And what that means is that after 1 second, I either have none or some item, right? I use an option. And the critical thing here is that these two are mutually exclusive, right? And the really interesting thing about this is now I've implemented timeouts in a semantics preserving way without modifying the pool at all, right? And that's only because the environment gives me this power to effectively express a mutually exclusive choice here, right? And so I'm guaranteed that either I received something from the pool or the timeout happened, right? And the environment makes sure that's true. And that turns out to be a very, very powerful thing to be able to rely on. So I'm going to finish with just to try to convince you guys that this is actually really, really useful and also a useful way of constructing concurrent software. I'm going to sort of go over a recent example in which we used these constructions. And so one of the things we do at Twitter is that we effectively store large server lists on Zookeeper. However, occasionally Zookeeper is unstable, either because the servers themselves are unstable, or there's a bug in the client libraries, or there's network issues. And what ended up happening is that if we relied sort of on the current view of a Zookeeper client of a particular cluster, which again is just a number of entries in you can think of Zookeeper as basically just giving you a file system, a distributed file system for the purpose of this. Then the resulting view of Zookeeper, the Zookeeper file tree, was very volatile, right? Which is not what you want in a distributed system where you want to have a stable view of your clients and all these different things. And this volatility was not because the servers themselves were volatile, they crash all the time or whatever. It's because of Zookeeper or Zookeeper client or network issues. And so the basic idea was, well, why don't we use the semantic of Zookeeper to sort of qualify these removals or additions of hosts. And so in particular, if I receive an event from Zookeeper saying host A has been removed, and I wait for some amount of time that's defined by Zookeeper to be the round trip time for heartbeats in Zookeeper, then I know that at that time plus RTT, Zookeeper was healthy at the time I received that remove host event, right? And so then I qualify it. And only then do I trust the fact that something was removed. So for example, if you have a healthy ZK, that basically just means, well, I need to time shift effectively the ZK events in this case. However, when you have flapping Zookeepers, I need to do something else. And so let's say we have a timeline like this where I first receive a remove host event, and then before the RTT expires, Zookeeper flaps. So it becomes unhealthy and healthy again. Well, what I need to do is to make sure that the view of Zookeeper is still consistent with the fact that A is removed after another RTT has expired, right? And so this represents an interesting sort of concurrent programming problem. You have all these events coming in asynchronously, you don't know when they're going to happen, and you have to maintain some state in terms of maintaining, keeping track of which hosts were removed at what time and what the shift is and so on. And so let's try to figure out how to use OperaBroker to solve this problem. Well, first of all, let's define two events. So connections can either be added or removed. And this is just a standard sort of algebraic data types pattern. And then I need a way to represent the events. By the way, one way of thinking about this too is that what we're implementing is basically just a filter that has the behavior on the right. So I receive the events on the left. I apply a filter that yields the behavior on the right. And so I need an offer for receiving all the input events. Right? I need a broker to send the output events, so this is the output of the filter. I need some sort of offer to receive updates of the health, and so that's the other sort of concurrent, non-deterministic asynchronous thing that happens in your system. You get health notifications in unpredictable fashion, and then the RTT is just a duration that defines effectively what the qualification period is. And so one common way of using OperaBroker is to effectively have loops with cases, just like you would in actors, for example. This is how we saw in the loop example in the semaphore as well. And so we can do effectively case analysis and break this problem in to the various cases. And the state, again, is the following. The state is the queue, which is the queued removals in this case. We don't care about additions. We can play fast and loose with those. And the current health of the cluster. So the first thing that we need to do is look at input events. And so in the case it's a remove event, then we recurse with a new connection with an expiry time of RTT from now. Right? If it's an addition event, I just immediately pass it through. But then in addition, if I see an addition that was previously removed, I've removed that queued remove event, right? And so that basically allows you to say, well, if I flap and the view of the Zookeeper cluster is not the same when it becomes healthy again, then I sort of reconcile that fact by removing the previous removes that turn out to be additions. If I receive a new health event, then well, first of all, if it's the same, then I don't need to do anything. If it goes from unhealthy to healthy, then I time shift all the events. And so basically I say, well, all of my queued removals, I'm going to wait for another RTT in order to qualify. And if I go from healthy to unhealthy, then I just change my state. So the next thing I need to do is, well, if I'm healthy or my queue is empty, right, then I don't need to do anything. Actually, that should be unhealthy. That's not. That should be unhealthy. If I'm unhealthy or my queue is empty, then don't do anything. So if I'm unhealthy, I want to delay all my qualifications. I don't want to alter the state of the cluster. Also, if I don't have anything queued, then I don't need to do anything. Otherwise, look at the first element in my queue and create a timeout offer when that event expires. And if that's the event that gets chosen, then I send that qualified event for removal further down. And this is effectively how I time shift all my removals. And so altogether, it just looks like this. This is roughly all the code that's needed to implement this. And we're dealing with a lot of hairy things here, right? We have all these different event sources. I have timeouts for when the time-shifted events needs to happen. I can receive health notifications from the cluster. And also events describing the additional removals of various connections from that cluster. And it's very, very powerful to be able to reason about these things as being mutually exclusive in this case, and also be able to have these guards basically saying, well, if I'm unhealthy in this case, then I want to wait until I'm healthy, for example. And it just turns out to be a very, very nice way of constructing solutions for these kinds of problems that exhibit great amounts of concurrency. So in summary, basically, what I hope to sort of get through with this talk is mostly to sort of communicate that there's a really rich history of concurrent programming. And threads and locks represent the sort of the very, very lowest common denominator for that. And unfortunately, it's the sort of in mainstream programming at least, that is the de facto way to go about programming concurrent systems. But there are far more powerful ways of thinking about them, in particular when you combine synchronicity, composition, events, and guards in particular. You get a lot of really, really powerful sort of emergent properties of that. And furthermore, everybody should read the CSP paper. It's a really, really insightful paper. And that's basically all I had to say. So are there any questions? Yep, over there.
Could you very quickly explain what you meant by offer and broker? Because the broker is also giving something and the offer is also giving something, or is one always the receiver and one always the sender?
So the question was explaining offer broker. What's the difference, basically? The difference is the following. So offers represent this abstract notion of an event in the system. And so this is the sort of thing that there's a number of offers in your environment, right? And your environment is responsible for effectively matching which offers can, together synchronize, right? And brokers are just a kind of a channel that allows you to produce offers from either sending something or receiving something. Right. And so you compose over offers. Brokers are just a mechanism for actually producing useful or coordinating these kinds of transactions.